Okay, so we've studied voltaic cells, and we've told you that electrons flow when you hook up a voltaic cell, which means it works like a battery. In fact, it works exactly like a battery. And if you're building a battery, one of the things you're very interested to know is how much voltage can it generate, so you know what kinds of devices you might be able to power with it. And we can find voltages for the reactions that we're doing with information that we have on our redox table. And the way you get started is you have to find what two reactions are happening in your solution. So in this case, they said we had a silver-silver side and a cadmium-cadmium side. So I've got all my chemicals here. And just to save us a tiny bit of time, I found our strongest oxidizer and strongest reducer already because I went to the data book and read down the left side until I found silver. And then I read up the right side until I found cadmium metal. And so those are the two reactants that are going to do things in this cell. We're going to have silver taking up electrons and turning into silver metal, silver ions into silver metal. On the other side, we're going to have cadmium metal turning into cadmium 2 ions and releasing a couple electrons at the same time. Now, off the redox table, if you look on the line for silver, the other information that's given there over here on the right is the voltage for that reaction. It turns out that the reaction of silver ions turning into silver has a voltage of 0.8 volts. That's called the cell potential or the reduction potential. For this, it's 0.80 volts. That's like a measure of how much the electrons want to do that reaction or how much they want to flow to make this reaction take place. We can do the same thing for cadmium, except there's going to be a little bit of a wrinkle. If you find your cadmium row, where are we? That's cobalt, that's not it. Here we are. Here's cadmium, and in the book here it says minus 0.40 volts. But that's for the reaction where cadmium 2 turns into cadmium. What we have is the exact opposite. We have cadmium metal turning into cadmium 2. If your reaction is running in reverse like this, cadmium metal to cadmium 2, that reverses the voltage too. So this reaction as written is minus 0.40 volts. Our reaction, where it's cadmium turning into cadmium 2, has a voltage of plus 0.40 volts. So if you're putting this one in, 0.40 volts positive. And what happens now is if we're adding these two reactions together, we add their voltages together. So for the reaction, or for the cell where you have silver ions and cadmium turning into silver metal and cadmium ions, the overall voltage will be 1.20 volts. That's how strong of a battery a silver cadmium cell would be. Now, I hope you recognize a lot of this from the thermochemistry unit, because in that unit we would also write reactions. When we were doing Hess's law, we'd write a reaction and it would have a delta H. And if you flipped a reaction, you would flip its delta H. That's true here. And when you added reactions, you would add their delta H's. So all those things are kind of the same, which is nice. Here's one important exception. Did you notice I fudged the electrons when I was doing this? This is only one electron and this is two, which means I should not have added this up the way I did. Let's fix that now. And as we do, I want to tell you one more thing about how voltages work. When you double all of these, I want two electrons. So I'll say twice as much silver, twice as many electrons, twice as much silver. Now here's an important difference from thermochemistry. Doubling a reaction like this doesn't do anything to the voltage. Do not double this. When we're doing Hess's law with delta H's, if we said twice as much chemicals, that meant twice as much energy. That's not true with voltage. So doubling all these, yes, do it, but it's not going to affect the voltage here. It's not going to affect the total down below. So the correct reaction here is two silvers and two silvers, but the voltage, I didn't do anything to that. Fair enough? Let's try a few more. carbon electrode, acidified potassium dichromate solution. Okay, let's get a list of our chemicals here. Acidified means we have hydrogen ions. That's what acid is. Potassium dichromate means we have K+, which I don't think is going to matter, and Cr2O7. We have an iron electrode. We have iron 2. We have sulfates, and we have water. So if we go to our redox table, let's clear away this older stuff. Acid dichromate is up here. It's one of the stronger oxidizing agents, and the voltage given for it is 1.23 volts. So we're going to have Cr2O72 minus, where is it, plus 14 hydrogen. I'm copying out of my paper data book now so you don't have to watch me flip back and forth over and over, plus 6 electrons. Produces 2 chrome 3s and 7 water and 1.23 volts. Now, our other reaction, I'll bet it's iron. SO3. Yeah, right here. Iron turning into iron 2. Now, as written in the book, iron 2 to iron, this has minus 0.45 volts. But our reaction is actually starting with iron and going the other way, so our voltage is going to be positive 0.45 volts. We have iron metal turning into iron 2 ions and 2 electrons, and that's positive 0.45 volts. Now, if I was going to write a total reaction for this, I would have to get 6 electrons in both of these reactions, meaning I'd have to triple the iron one. So when I do that, you get 3 times as much iron, you make 3 times as many ions, you go through 3 times as many electrons, but no change on the voltage. The overall cell voltage for this is just going to be 1.68 volts. There is another way that people are taught to do these sometimes, where they tell you to do the cathode reaction minus the anode reaction. And yes, that works. And if you feel like using it, go ahead. I don't like it. I find it's hard to remember, and I just don't have that much spare space in my head. So I think this one is smoother because it's similar to stuff you've already done in thermochemistry, and the rules for it mostly make sense. If you flip a reaction, flip its voltage. If you add 2 reactions, add their voltages. That's logical enough. The one thing you have to remember is that unlike in thermo, if you scale up an equation, you do not scale up its voltage. All right. So if you're doing cathode minus anode, by all means, go ahead, and I'm confident you'll come up with the same answers as me. I just hope you remembered in the right direction when you get to the test. I was never able to find a good way to get that one to stick in my head. Platinum electrode means inert electrode, means who cares, it's not going to do anything. We have hydrogen gas. We have hydrogen ions, meaning acid. We have zinc. We have zinc ions. And off we go to our redox table. Hydrogen by itself is right here. So the forward reaction or the reduction reaction is hydrogen ions reducing to hydrogen gas, and that's listed as 0 volts. So our first reaction is 2H pluses plus 2 electrons turns into hydrogen gas, and for that 0.00 volts. The other one, not surprisingly, is zinc metal turning into zinc 2. Zinc is our strongest reducing agent, so for this reaction we get zinc metal, it turns into zinc 2 and 2 electrons, and the way they write it is zinc 2 turning into zinc, and that's minus 0.76 volts. But ours is going the other way. We're writing this reaction flipped, which means we get a flipped voltage, positive 0.76 volts. And now when we add these together, the electrons match, nice. So our overall reaction is two hydrogens jump a zinc atom and take its electrons. The hydrogen turns into a gas, the zinc ionizes, and if you made a zinc hydrogen battery, it would produce 0.76 volts. Okay, a couple more. Copper electrode, copper 2, nickel electrode, nickel 2. Okay. I know copper's higher than nickel. Copper is right here. It's written as copper 2 picks up 2 electrons and turns into copper. And nickel is not that much lower, right here. Okay, so for the copper reduction, we have 0.34 volts. Volts. This reaction is a reduction. If they ask about electrodes, that would mean it's happening at the cathode because reduction and cathode both have a C in them. And the other reaction is nickel oxidizing like so. This would happen this is an oxidation, which would happen at the anode because oxidation and anode both have an A in them. And for the voltage, nickel is supposed to be minus 0.26 volts, but we're doing it in reverse. We're starting with nickel, so our reaction is flipped. That means our voltage is also flipped. It's positive 0.26 volts. And so this negative here belongs to the electrons, not to the 0.26, just to be clear. So when we add these reactions together, the electrons already match, so no need to adjust that. This is our overall cell reaction. And our overall voltage is 0.34 plus 0.26, which is 0.60 volts. Okay, last one. Carbon electrode. Carbon is inert, so it doesn't do anything, so ignore it. Is in acid permanganate. There we go. And then we have lead and lead 2 and sulfate. Okay, so I have a pretty good idea what I think is going to happen here, but let's look it up and make sure. Acid permanganate is one of the great champions of oxidation. It's very, very high. Right there. Voltage 1.51 volts. And if we go up the other side, we have lead and we have sulfates right here. Lead metal and sulfate ions can convert into lead sulfate like so, and that is minus 0.36 volts. So let's get those down. Acid permanganate. This is the easy part. You just copy it out. Plus, is it 5 electrons? Yeah. And that produces manganese 2 and 4 waters. And according to the data book, the voltage for that is 1.51 volts. And the reverse reaction is lead metal meets sulfate ions and produces lead sulfate and 2 electrons. In the book, this is supposed to be minus 0.36 volts, but since we wrote it in reverse, positive 0.36 volts. When you flip a reaction, you flip its voltage. Now, I want to match up my electrons here, and 5 to 2 is a little awkward. The lowest common multiple for these guys is 10. So to get 10 electrons, I'm going to double the first reaction. twice as much, twice as much, twice as much, twice as much, twice as much. And I'm going to quintuple, multiply by 5, the second reaction. Times 5, times 5, times 5, times 5. And notice, didn't change the voltages. Voltages don't care if you do this. Changing these numbers means your battery may run out sooner, but that's not what this number is about. This number is while the battery is at full power, how much voltage will it deliver? So that's the reasoning behind these numbers changing, not affecting the voltage. Having more chemical doesn't mean you get more volts. It just means you get that same number of volts for more time. In this case, twice as long. Or if you add twice as much chemical, you'd have that voltage for twice as long. So there's our two reactions. And the overall reaction, if you add these together, I'll spare you writing all that out again, but I do want to get the voltage because that's the big important thing. 1.87 volts is what this cell would deliver. This reaction is a reduction because it's gaining electrons. That means it happens at the cathode. So just to get that down, this is gaining electrons. There they are. Leo says GER means gaining electrons is reduction, and reduction has a C in it, so it happens at the cathode. This reaction loses electrons, because there they are, sitting there afterwards. The chemicals gave them up. So that's a Leo. Losing electrons is oxidation. Oxidation has an A in it, so apparently it happens at the anode. Easy.